Reading a barcode looks effortless, but underneath that familiar beep is a highly complex mathematical deconvolution problem that bridges optical physics and digital symbology. The push for automated tracking began in the late 1960s. The North American railroad industry struggled to manually log millions of moving railcars. In 1969, an engineer named David J. Collins introduced the first machine-readable solution, the Automatic Car Identification System, or KarTrak. Instead of black and white lines, KarTrak used red, blue, and white reflective stripes on the sides of trains. As the cars rolled by, the system blasted them with 500-watt xenon lamps and used highly sensitive photomultiplier tubes to capture the reflected light. The engineering vulnerability was the physical environment. Train cars are exposed to rain, dirt, and harsh sunlight. Over time, the color-coded stripes faded and collected grime, steadily degrading the optical signal until it became unreadable. Even when sensors captured a signal, processing that messy analog data required massive mainframe computers, which were financially impractical for many companies to maintain. Strangled by these technological hurdles and concurrent industry bankruptcies, the railroads officially abandoned the KarTrak system by 1978. The demise of KarTrak demonstrated that physical environmental noise mandates a high-contrast, error-tolerant mathematical solution rather than an analog color-based one. Recognizing the failures in the rail yards, the grocery industry began pivoting in the early 1970s toward high-contrast binary systems. A team at IBM, led by George Laurer, developed the numerical format and design that would become the Universal Product Code, or UPC, in 1973. Relying on a strictly black and white grid solved the color degradation issue. Black bars absorb light, while white spaces reflect it. This contrast is highly durable and can be printed accurately on almost any material. This specific format was put to the test on the morning of June 26, 1974. At a Marsh supermarket in Troy, Ohio, a 10-pack of Wrigley's Juicy Fruit Gum became the first UPC-marked item ever scanned at a retail checkout. That single scan validated the viability of laser-based scanners and black and white barcodes for high-speed, high-volume retail commerce. Moving from colored stripes to the UPC replaced analog approximation with digital certainty, setting the standard for inventory management for the next 50 years. To read those black and white bars, modern scanners execute a 4-step physical hardware pipeline in the fraction of a second it takes to hear a beep. First, a high-intensity light source illuminates the barcode. Second, a precision lens collects that reflected light and focuses it. This creates an immediate optical challenge. If you bounce that light off a standard glass mirror, the dual surfaces of the glass create double reflections, or ghosting, which corrupts the data. To prevent this, scanners use first surface mirrors. By placing the reflective coating on the front of the glass rather than the back, the scanner ensures a single, perfectly sharp optical bounce. Step 3 is the sensor. Through the photoelectric effect, the sensor array captures that clean reflected light and immediately converts varying light intensities into fluctuating electrical currents. Finally, step 4 is the digital decoder, which interprets those electrical currents and converts them into a clean binary sequence. Perfectly engineered physical optics are the mandatory prerequisite here. If the hardware fails to capture a crisp optical reflection, the decoding mathematics have nothing to process. This chart maps a digital waveform directly to the linear barcode beneath it. A scanner doesn't see black and white lines. It sees discrete binary modules. A complete UPC-A symbol is constructed on a precise grid that is exactly 95 modules wide. That grid holds 12 numerical digits. Every single digit occupies exactly 7 modules and is always composed of exactly 2 bars and 2 spaces of varying widths. The grid also contains non-data timing elements.
These are the start and end guard patterns, which are 3 modules wide, and a 5-module middle guard pattern. These anchor the scan and establish the timing. To ensure the scanner reads the digits in the correct order, regardless of orientation, the UPC standard uses a mathematical concept called directional parity. The logic works like this. Digits on the left side of the middle guard are encoded to always have an odd number of black modules, giving them odd parity. Digits on the right side always have an even number of black modules, giving them even parity. Through this inversion, the scanner's logic gate instantly detects its read direction. If it hits even parity digits first, it knows the barcode is upside down, and it simply reorganizes the data into the correct order. The final safeguard is the check digit at the very end. Calculated using a modulo 10 algorithm, this number allows the system to instantly detect single-digit scan errors or transposed numbers. The brilliance of the UPC symbology is that it embeds its own self-correction and spatial orientation instructions directly into the physical data payload. In a controlled environment, reading this grid is simple, but real-world scanning environments almost never provide a pristine 95-module target, forcing scanners to mathematically reconstruct degraded signals. Modern decoding tackled this as an inverse mathematical problem, mapping a messy optical signal to a sparse representation within a known dictionary of barcode symbols. This formula represents the governing deconvolution equation used to isolate the barcode. It is defined as D equals alpha times G of sigma times C plus H. To find the true binary code, represented by C, the system must strip away physical distortions. It calculates the ambient light multiplier, alpha, the Gaussian blur matrix based on distance, G of sigma, and the additive noise, H. Over the decades, scanner hardware has evolved specifically to provide cleaner raw data to these algorithms, beginning with traditional laser scanners. Lasers sweep a beam across the code using oscillating mirrors, but moving mechanical parts are prone to breaking, and lasers physically cannot read barcodes off digital screens due to backlight interference. This led to charge-coupled device, or CCD scanners. These capture a solid-state, one-dimensional electrical slice of the code. They have no moving parts, greatly increasing physical durability, though their read range remains narrow. The current standard is the CMOS 2D imager. These operate like digital cameras, instantly capturing full image frames and using grayscale binarization to read complex two-dimensional patterns like QR codes in any orientation. Transitioning from mechanical lasers to solid-state CMOS imagers shifted barcode scanning from a mechanical sweeping challenge to a pure image processing problem. The sheer scale of this hardware-software integration is immense, operating seamlessly in high-stakes environments where speed and accuracy are non-negotiable. Retail point-of-sale systems, global logistics tracking networks, and healthcare patient wristband protocols all rely on this exact mathematical translation millions of times a day. For extreme environments, modern CMOS imagers now layer artificial intelligence on top of the raw optical capture. Machine learning algorithms allow camera-based scanners to dynamically isolate barcodes in visually cluttered backgrounds, identifying the target pattern instantly, even while completely offline. But there is an absolute failure threshold. Eventually, physical damage to the barcode will exceed the mathematical recovery limits of the Gaussian blur algorithm. When that happens, scanners utilize the ultimate software redundancy, optical character recognition, or OCR. This allows the scanner to bypass the bars entirely and read the human-readable text printed below them as a fallback. The barcode scanner's 50-year evolution, from fragile colored stripes on train cars to AI-driven image processing, proves that true engineering resilience is achieved only by combining foolproof mathematical standards with adaptive software.